let's get started. So now we're going to move into a new part of our course, which is essentially going to talk about linear models. So we have to get one linear model earlier, which was set. So when I say linear, it essentially means that you have data which is expressed into, which is represented as a d-dimensional vector, right? So you have d attributes that describe this. And then the learning algorithm does a linear combination, right? Whenever you see W transpose X, which we have been looking at from human time, then that makes it a linear model, right? So we're going to start with something called a linear Gaussian system, which is not really a linear model, but it kind of helps set the stage for regression later on. Then we're going to talk about regression, which is one form of machine learning task where you want to predict a continuous value instead of a discrete attribute. And then we're going to move to logistic regression, another linear model, but that is used for classification instead of regression, right? And then we're going to then sort of expand that to handle non-linear cases, and then we'll talk about kernel methods and support recognition, right? So all fun things in part C. So let me start with some basic notions that we're going to use often. So I hope that you're familiar with that. So often you would hear the term of statistical inference or inference in machine learning, right? So inference is, in general, it means that you are given some partial information and then you want to find out the rest of it. Right? So even classification can be thought of as inference. So you know your inputs and you want to find out what your output is. In statistics, because they're dealing with probabilities, inference means you want to find out the probability distribution of what you have not seen. In many cases, that is the class table, given your training, given your input, x, right? So that sort of is inference in general. However, inference is much more than just classification, right? So if you have any probability distribution, so let's look at this probability distribution in which you have two random variables, x1 and x2. Right? So inference could mean what is the probability distribution of only x1. Forgetting all about x for any value of x2, what will be the probability distribution of x1. And it could also mean computing the conditional distribution, which is what is the probability distribution of x1 given x2. Okay. So in your midterm, you had one problem about probability table and it's kind of like. So I have an example here. So let's say you have two random variables, right? In this case, it's x and y, right? Here we are assuming that it is discrete, which means that both x and y take finite number of values. In this case, x takes 4 values, 2, 3, 4 or 5, and y takes 2, 3 values, 0, 1 or 2. Semantically, here in this example, we are assuming that x means length of a word and y means number of vowels in the word. Right? So this is the joint probability distribution. And whenever we talk about joint probability distribution of categorical or discrete variables, it essentially is a table. It is a table which enumerates all possibilities. So it tells you probability of capital X to be 2 and capital Y to be 0 is 0 and so on. Right? So that's a joint probability distribution. Sometimes you might be asked to find the margin. Right? So you might be asked to find what is the probability of X for all values of Y. Right? So that typically is done by just summing over all possible values. Right? So this vector here is the probability distribution for x. That's a marginal for x. Right? Because remember, a probability distribution is basically enumerating probabilities of all possibilities. Right? Now x can take 4 values, right? 2, 3, 4, 5. So this distribution is the margin. Right? If you want to find conditional, so for example, if you want to find the probability of x given y is 0, right? So then you just choose this row. If this is the distribution of x, then y is 0. So that is the difference between marginals and conditional. Right? What happens later on, and we'll see the other aspects of machine learning now, is that most often x and y are not discrete, but they are continuous. Which means it's not possible to express the joint probability distribution as this, because each, let's say x and y were continuous, then x could take infinite value, y could take infinite value, right? So in that case, instead of expressing it as a tail, which is not possible, you would express it as a probability function, right? So you would assume some power of the joint distribution and then use the random to express it. Alright? So that is, I mean, you might feel why we are looking at this right now, but that's just to set the state of the picture. Any questions so far? Okay. So as I said, then the joint distribution essentially is a distribution in which you have many random variables, right? So we have looked at something like that in 9 ways, where we assume that the x, right, the inputs have d attributes. So you can think of it as a joint distribution, right? So if each one of them is a Gaussian distribution, if each one of them is a continuous variable, right? So x1 is some value, let's say I, so it's continuous. X2 is something else, weight, and so on. Then you can express this. One way to express this is to model it as a multivariate curve. We have looked at that, right? Now what we can do is we can compute marginals here as well. So you can compute the probability distribution of x2, marginalized over all other variables. Or you can compute conditionals. So you can compute x1 given x2. Right? So you can compute all of that. And what happens with Gaussians is that marginals and conditionals are also Gaussian. That's sort of the nice property of a Gaussian distribution. So for example, here we are considering that we have two random variables, x1 and x2, right? And we are assuming x1 and x2 are continuous numbers. So the joint distribution of this x, which is the collection of these two, we can model it as a two-dimensional Gaussian distribution, which means its mean will have two entries, mu1 and mu2, and its sigma can be broken down as this. Right? Sometimes you also use this here, the capital lambda or case lambda, which is essentially the inverse of sigma. So if you remember the Gaussian distribution, oftentimes we work with the inverse of the covariance matrix. Right? This is also known as the precision. So the covariance tells you how much is the variance along each dimension. Precision tells you how much is the sort of precision there, the inverse. But it's the same. It turns out that if you do the math, right now it's easy to do this math in the sense that if I want to compute P of x1, right, how would you compute it? What you would do is that marginal, oh gosh. So if you have a random variable which has two variables inside it, right, x is this, and x is a multivariate Gaussian, right? It has some new vector, and it has some covariance matrix, right? So which means that probability of the joint probability distribution x1, x2 is given as our standard form, which is under root pi, square root of pi, determinant of this covariance matrix times minus f x minus. So let's consider this as x, right? It's a vector x. So x minus mu transpose. Right? Now, if I want to compute the marginal of x1, just x1, right? What I would do is I would sort of marginalize over all possibilities of x2. Right? So if you go back here. When I asked you to compute the marginal for this discrete distribution, the marginal all you did was you summed up these values, right? Now, in our case, what will happen is our other variable is actually infinite dimension. I mean, it can take infinite value, which means that instead of summing up, you will do an integration, right? So it turns out, without going, what you will do here is you will basically do integration over all values of x2 and dx1, right? And where this is essentially this problem. So it turns out, because the Gaussian distribution is such a nicely formed distribution mathematically, that if you solve this integration, that will also come out to be a Gaussian. Right? And that's exactly here. So in fact, if you compute the marginal for any one of this would just be Gaussian with mu1 as mean and sigma 1 as part of the covariance matrix as the covariance. And you can also compute the same way you can also compute the condition. What is the probability distribution of x1 given some value of x2? That also turns out to be a problem, right? We will not go into the math that much, that's too detailed. But I think the main thing you want to remember is this, that for a Gaussian distribution, if you have a joint Gaussian, then the marginals and conditionals both are also Gaussian. And you can compute the means and covariance, right? In fact, I think we'll make use of this later. Any questions so far? Okay. So now we will look at something called a linear Gaussian system, and you will understand why we are looking at it, and then we'll move on into linear regression, right? So I'm going to motivate a linear Gaussian system by an example. So 2 years back, if you remember, there was a plane that went missing in the South of Central, I think, the Malaysian Airlines plane, right? So think of the problem as trying to locate the error, right? We don't know, so let's assume that this is sort of the 2D view of the ocean, and the plane can be anywhere, right? We want to find out where it is. Now, the data that we are getting in are some radar clips. So there are some radars on the satellites or somewhere, right? So they are basically trying to catch any signals coming from the aeroplane. So every time you get a signal, right, you say, okay, maybe the plane is here, maybe the plane is here. But the problem is that those signals might not be accurate, right? Many reasons. For example, the sensor might be faulty. The second is there are environmental factors, rain, wind, and storm, and everything, right? So you're getting all these noisy measurements, and you want to estimate the exact location of the error, right? So you can think of that problem as a linear Gaussian system. So think of these as these different measurements that we are getting, right? So one easy thing we can do is, once we get the first, let's say, so the radar tells us that it is here at 2.3, right? We can say, okay, the plane is at 3, right? But next time you get that the plane is actually at 4.24, and next time you get it is at 3.3. So after all of this, maybe what you can do is you can take an average, right? That's a very simple solution. Another thing that you can do is you can think of each of these measurements as a two-dimensional Gaussian, right? So think of latitude as one of your random variables and longitude as another random variable. So you can model it as a joint Gaussian, and then you can compute the mean and covariance of this set of information that you have, right? And that will give you the MLE using things that you've done in the past. So what you can say is that the actual location of the aeroplane is not an exact value, but it's a distribution. A distribution whose mean is essentially going to be the mean of these values, and covariance is going to be the sum of the information, right? So we can do that. However, what else can we do? Right? How can we also incorporate information such as, let's say we know how much the noise in each sensor is, right? Let's say we also know some prior information about the location. How can we incorporate all of these, right? So that's essentially this problem, right? So what I told earlier, you can think of it as a frequentist approach. And you have some observations, and then you just take an MLA of that and get that location. But in a Bayesian setting, what you can do is you can think of the actual location of the aeroplane as some hidden value. That's the true value that you can, but you can't measure it. What you measure are some noisy versions of that true value, right? So let's model it as y, right? And let's say each radar flip, the observation that you make, let's consider that also as a random variable x, right? Now what happens here is that x is generated from y. So if you think of it as a generative process, now y is the true location. Let's say this is the ocean, right? So think of this, let's say this is y, so the plane is over here, right? But when a radar measures it, what essentially happens is this y gets corrupted a little bit, right? So maybe because of the sensor noise and the environmental factors, the x is somewhere here. So you can think of it as the x is being generated from y by corrupting it a little. So y is precise actual value, and x is what you measure. However, the problem is we can only observe x, right? We don't observe y. So it becomes what is known as a backward problem. So the forward problem might be easy, right? So for example, you might know what the sensor dynamics are, and you might know what the how the environmental factors behave, right? So you can actually calculate precisely what would be x if y is some, right? So you might so that is called a forward problem. Is that given y is the true location. Compute x. This can be done exact. Why? Because you can take the y and you can, if you know all the physics that goes in and all the other things, all the mechanics, you can compute what x will be by applying some formula. Right? However, what the interesting problem is what we call the reverse problem, which is given x, find y. Right? Now this cannot be done exactly, right? Because you don't know how the pattern works. And that is why we call that the inference problem. We infer the y given x, right? And that is what we are going to do with this linear Gaussian system. Any questions about it? So to do that, what we do is we model both y and x as Gaussian distribution. We assume that y has a Gaussian prime, which essentially is breaking some domain Gaussian. Let's say somebody tells you that the true location, without knowing anything else, is that the plane is at 2.5, 2.5, and it's going to be in a circle around 2.5. Let's say that's sort of the prior information. You can model that as a Gaussian, right? You can create a Gaussian variable prior in which the mean is 2.5, 2.5, and the covariance matrix kind of determines this size of this circle. Right? So you can do that. And then what you assume is that each x, right, each observation that you make is a normal distribution centered at y with some covariance matrix. Okay? So this kind of tells you, this kind of encodes the error in the sensor. Right? So what you say is that the xi is generated by taking the y, the true location, and adding some noise. So that is the forward process. Right? Now our job is, given some xi's, x1, x2, x3, some locations, we want to infer posterior for it. So we already know the prior for y. We already know that y is centered here with some covariance matrix. Now we want to define it by taking some observations, so noisy observations, right? So this is sort of pictorially that. So think of this again as the ocean, right? And the prior tells you that your y, the true location of the aeroplane, is somewhere here, and this is the covariance matrix. So it's, you're still not, prior is not a precise information. Right? So you're not saying it's here. You're saying it could be anywhere here, but with this problem. That's sort of a easy way to set the problem. Right? Now what you want to do is, by making some observations, by looking at some observations, you want to change this distribution. You want to change it to the posterior. Okay? So linear Gaussian system lets you do it. Right? So in general, so the motivating example that I'm giving you is a simple form of a linear Gaussian system. Right? So a linear Gaussian system, in general, can be thought of this. So you have some true observation y, right? You set some prior event like this, and then you have some measurements, something that you measure, which are essentially another random variable which is governed like this. So x is some linear combination of y. So y can be a vector, right? So A is a matrix. So what you do is you multiply a matrix with this kind of vector and add another vector. This is a standard way of doing linear combination. Right? So if you have this, then what you want to do is find the posterior, find field y given x, right? So that is a general sort of a linear Gaussian system. You're assuming that what you observe, the x, is some linear combination of y, and b. Let's assume we already know what a and b are. We know how the inputs, how the true value gets converted into the noisier, right? Through this process. Right? Now what we want to do is, after observing some of these x's, we want to refine our problem. We want to find posterior. So if you go back to the previous example, in the previous example, essentially what we assumed was that A is identity and B is same. So we are just saying P of x given y is just a normal distribution centered at 1 with this. But in general, Gaussian, linear Gaussian systems, it could be any. Right? So you can think of it also as sensor fusion. So you can think of it as you have some sensors, many types of sensors, and this is how the sensors are getting combined to form the output. Right? So if you work in those areas, like this is something that will be familiar. But the idea is this. So this is a standard Gaussian system, and then you can compute these values. Okay, and that is why what I showed you earlier about how the conditional and marginal of a Gaussian is also a Gaussian, that helps you. So what we need to compute now is Py given x. Right? So how we do that is just by applying our good old base rule, right? So we have P of y, this is the prior, which is a normal distribution with some mean, some covariance matrix. So this is the initial estimate that you have for your rule of inference. And then you have Pxy, which is sort of how this is converted. So this is a y plus b. So this kind of tells you what is your faith or some confidence in the sense. Right? So this is attached to this. And then so we assume that we know all of this. We know A, we know B, we know this. Right? So our job is find the posterior. Py given x. Right? So mathematically you can do it by applying Bayes' rule. Right? You can say this is x given y times Py. And since this is a continuous random variable, since you have the summation here, we'll just do a thing here. Over all. Right? Now we are not going to do this today, but based on the results that we saw earlier, it turns out that this is also going to be a Gaussian. Right? Why? Because of this, the property of a Gaussian system. So this will also be a Gaussian. Right? And in the slides, I have given you the exact formula, the new mean. So whenever they say that a new variable is going to be a Gaussian, it means that it will have some mean and some covariance matrix. Right? So that will be given by this. So this is the new covariance matrix. And this is the new group, right? So you don't have to really look at it very deeply, but that's sort of a standard formula. If you're very adventurous, you can derive it, but you can take this as a result. All right. So which means that if I want to apply this kind of methodology to locate the airplane, right? So in the airplane example, what we are assuming is that our A is identical, right, and our B is C. So this becomes a little simple. Your new covariance matrix will just be the sum of this plus sum of this, or plus this, right? Because A is identical. Right? And the new mean will also be a simple factor. Right? So you can use that to compute the. So I have and then you can look at this formula. So that's the formula that I have. But I have a sort of a work here. Right? Let's look at it. So let's say that this is our, the ocean, right? And right now, this gives you the prior, right? So what this is saying is that I believe that the aeroplane is at 0, 0. It's like a weird example, but let's assume that latitude and longitude get both. Like this is it's actually that's fine. So this kind of tells you what is your prior distribution. So these are what we call contour. Right? So dark means that the probability is high here, and then as you go up, well, not dark, but the color is increasing. As you go farther away, the probability goes down. Right? That's the standard Gaussian. So this is our new estimate. Then what we do is we make some noisy observations, right? And then we apply those formulas here, and every time we define our estimate. Okay? So if I run this here. Actually, what you see here is that initially you assume that your y is over here, right? After you see the first example x, which is let's say 1.4112, then what will happen is that this will move. The distribution will move. You are computing the posterior, right? So what happens now is that the distribution will move a little bit, and its covariance matrix has also changed. Then as more and more data comes in, your posterior sort of keeps moving. Right? So that's the idea. And that's it. So that's sort of the notion of a linear dynamic Gaussian system. So this time in gradients, what you will see is you'll have a problem like this. Okay? So I've given you an aeroplane prior location. So I've given you what sigma naught is and mu naught is, and then I've also given you a bunch of observations and given you the sensor nodes, and then you need to compute the new estimate. You can compute the new posterior curve, right? You got it so far? Yeah. Right. Okay. Good. So in the past, and that's what you will see in your assignment too, is we were trying to learn these discriminant classifiers, right? So we were trying to see, okay, so we had two classes of points. So we were doing classification, right? And you had a bunch of points. Some of them belong to class A, and some of them belong to class B. And we were modeling each of those classes as a Gaussian. So then what we were computing was, for each set of points, the Gaussian, the MLE for that each class. And then we were trying to predict the new class, given certain location, right? So there, the problem was set up like this. So this is what we call discriminant analysis. Right. So what we did was we said that your y, right? So we said that we have two types of points. We have class A, and you had some other class B. So what we did was we said that the probability, we computed two probability distributions. One for only the positive class, or the first class. And we said that that is given as the probability of x given y is equal to 1. So let's call this y equal to 1. Y equal to 0. Given y equal to 1 is a normal distribution with some mean and some covariance. And this you can estimate by doing it. Right? And the other one you said that y equal to 0. And you can use that as well. And then what you do is, given a new data point, x star, you can compute if it's y equal to 1 or star y applied base rule. Right? So you can say, and then you also assume some prior distribution. So this is more of a classifier. We're trying to predict a discrete value for it. In what we are doing right now, we're not doing any kind of classification. We are trying to infer the true value, or hidden value, by looking at some noisy linear combinations of the data. So it's a different problem. Okay? Here, if you set these to be equal, right, that is known as a linear discriminant analysis, LDA. And if these are different, then you set for it. So in your programming assignment, you will have to implement each one of them. LDA means sigma 1 is equal to sigma 2, and then when you do the assignment, you will understand why it is linear program. So anyway, so that's sort of the difference. Right? That makes sense. So here what we are doing now is that for in the case of a linear Gaussian system, we are trying to, so now the thing that we are trying to predict, the y, is actually not a discrete value, right? So we are trying to do more like a prediction of continuous value, given some noise, right? So this is sort of the expression for a posterior of y, given, assuming that A is identical to B. So this is just that airplane example. But this is actually a very, very interesting approach, because what you can do now is you can think of each one of these sensors, right? So you can assume that each one of these noisy observations are coming from different sensors, right? And each sensor might have a different sort of an error. So instead of using the same error, in this example we are assuming each radar sensor has the same error, but you can assume different error and you can combine. So it's pretty sort of interesting. And then this goes on to become, if you are coming from an engineering background, this goes into the control systems literature where we talk about linear dynamic systems, we won't cover that here, but essentially this is sort of the core or the first step towards those methods. Right? Any questions? So first, this is actually we call sigma. So this is the covariance matrix, right? And this essentially means the inverse of this covariance. So when we are saying that you're trying to compute the posterior probability distribution for y, what it turns out is that this is also going to be a Gaussian. So this is the mean and this is the covariance. So that's how the math works. So when you do the integration here, right? When you do this integral, when you solve it, it will turn out that the new mean and covariance will have that. Right? So, I mean, I'm sort of skipping all of that, and that's sort of not within the scope of this course. But essentially, what this is saying is that the inverse of the new covariance matrix is equal to the sum of the inverse of the prior and n times the precision of each redundant. Right? So now let's move on to our next topic, which is linear. So in linear Gaussian system, we assume that we wanted to find y, right, given x, right? But we assume that we don't know what y is, right? But what we know is how is y related to x, because here we are assuming that y and x are related by this equation. Okay, so we already assume that we know what a is and we know what b is, and now we want to do the inference. In linear regression, what happens is we say that we don't know what that combination is. Okay? So we don't know what the a and b are, but what we know are some pairs of x and y. That's our training data, and we want to learn that. So it's sort of a slightly different problem. So in a linear Gaussian system, we assume we know what a is, what b is, and we want to find b, y given x. But in a linear regression, we don't know what these are, and we want to compute those. We want to learn those. Okay, so that next time I see a new y, I can compute. Next time I see a new x, I can compute. So it's slightly different than linear Gaussian system, right? But very similar idea. So what we assume in linear regression is that we have one target variable y. Okay, and a lot of you might be familiar with regression, so that's why I use very common terms here. So we have some target variable y that we want to predict, and we have some vector input x, right? So it's very much like the classification we've done before, but instead of predicting a class, right? Instead of predicting what digit this is, we are trying to predict some value, like some real value. Okay, so that's a linear regression approach. And what we want to learn, the learning part is that we want to learn some weight vector given a set of training examples. Okay, so now let's. We want to be a little. Yes. Now we are saying linear regression. In linear regression, we assume that we have some y, that y is a scalar value, and we assume that y is a linear combination of x. Okay, so x is a d-dimensional vector. So this is the inner product, right? So this is a linear combination of all those dimensions. Think of it as x, and these d numbers, and this w also a d-dimensional vector. And then what you're assuming is that y is basically you're taking the weighted combination of all x. That's a standard formula. So the learning task means that I give you some training data. So I give you some bunch of x's, some x1, y1, x2, y2, and so on. And I want you to know. I want you to learn them. What will be the best level? Right? So that's slightly different from linear Gaussian system. Okay? So one thing that we typically do in linear regression is that we combine all of these, okay, of your training data into a matrix called X. We call this the input matrix. So each row of this input matrix will be one of the observation. So this input matrix will be n cross d, right? Because it has n observations and d data. And we also combine all of them into one long vector called y, and this is the target vector. And of course, this will be n cross d. So the linear. I think I use a small. Linear regression learning task is given x comma y, the input matrix and the target vector, learn them. Why do we learn them? Because now, if I give you a new x star, you can, given x star, I can predict y, x y star, which is later. So that's the linear prediction. Right? And it has uses in many things. It's easy to imagine how useful this technology is. So there are two ways to interpret linear regression. Okay? So one is probabilistic interpretation, which is sort of comes, which we will sort of focus on. So here we assume that y is essentially a noisy linear combination of x. So this is the so we don't assume that x is a random variable. Here we assume that only y is a random variable and y is essentially a noisy combination. So it's a Gaussian distribution which is centered at w transpose x. Right? So remember, w is d cross 1, x is d cross 1. So this will be unstable. Right? So y is a univariate Gaussian distribution centered at this with some probability, with some variance. This is a fundamental. Right? So our task is to learn w and sigma square. Or we can also think of it as we assume that y is w transpose x plus some noise. Some noise which is centered at 0. We also call it white noise. It's centered at 0 with some sigma square. So y is a linear combination, noisy linear combination of input variables. And our task is, once we learn w and sigma square, then we can find the probability of y given x. Right? So now, if I give you some input x, right, you can feed that in here. You can compute the posterior probability of y given x. Okay? Any questions so far? Then there is another interpretation for linear regression, which comes from line fit. So if I give you a bunch of points, like in a two-dimensional space, and I ask you to fit a line, then that is also that is the same effect. Right? So if you have so let's go. So think of this, right? So if I give you a bunch of points, right? So this is your x and this is your y. So what you want to do is you are given this training data. You can think of it as training data. You want to fit a line straight because the effect of w transpose x is something which you are fitting a line. Such that now if I give you a new x, you can predict what y is. Right? So that's the linear interpretation. This is the geometric interpretation of linear. So we assume that d is 1. Right? So, and we say that y is w transpose x. But since your w is just a one-dimensional vector and x is also one-dimensional, you can think of it as wx. Right? So learning this w essentially means trying to fit a line. I have 2 points. So your x is to y. This will be the equation of this will be given by this y. So now what you can do is if I give you a new x star, if I ask you what will be the value of y and x star, you can essentially take this, that if you just learn it like this, right, you are forcing this line to always go to the origin, right? Because any line which is y equal to 4x, y equal to 5x, or anything, will always pass through the origin. But that's something that you might not want. Right? For example, if your data looks like this, very nice linear data. So data, you don't want, I mean, a good line would be this, right? But this won't let you learn. Right? If your line is y equal to something x, then it has to go through. So what we do is, to be able to learn lines like these, we introduce intercept, right? Just like we do in perceptrons and neural network, we add an intercept, which essentially means that we add another variable to x, another dimension, which is of 1. Right? And so then what happens is that adding intercept, right? Adding intercept is done so that the line can pass, so the line does not have to pass. So what we do is, your x essentially becomes whatever your x was, n of 1, right? And now your w would be all the w's that you have. Well, this is standard. I'm going to add the intercept at the beginning. It doesn't really matter. And then what happens, your w basically becomes whatever your w was, n of w. Right? So now your y becomes w naught times 1 plus w times 1. So now this line will not back, doesn't have to pass. Right? So that's just how you make this line not pass. So from now on, whenever I talk about linear regression, we will assume that we have already incorporated that intercept term in your text. Okay? You got to go back? Okay. So now comes the question. So I will talk about this. Now comes the question, how do we learn this stuff? Okay, this is our core machine learning problem. Given some training data, how do we learn this stuff? Right? That is done. There are many ways to do it. We'll look at 2 ways. Actually, we'll look at 3 ways. So one is using maximum likelihood estimation. Second is using least squares approach. And third is using a graded descent. Okay? So we'll look at one by one. Start this maximum likelihood. Right? So this is just the result, final result. I won't go through the actual math here. Read that.